Welcome everyone to the Cartesian Cafe. I am your host, Tim Nguyen. Today, we're very lucky to have Marcus Hutter here with us. Marcus is an artificial intelligence researcher who is both a senior researcher at Google DeepMind and an honorary professor in the Research School of Computer Science at Australian National University. He is responsible for the development of the theory of universal artificial intelligence, for which he has written 2 books, one back in 2005 and one coming right off the press as we speak. Marcus is also the creator of the Hutter Prize, for which you can win a sizable fortune for achieving state-of-the-art lossless compression of Wikipedia text. Welcome, Marcus. How are you doing today?
Hi, Tim. I'm fine. Thanks.
Yeah, great. I'm glad I'm finally able to interview one of my colleagues at Google DeepMind. Of course, it goes without saying that everything we discuss is reflective of our own thoughts and opinions and not those of our employers. That being said, before we dive into the details of what will be a very fascinating topic, why don't we talk a little bit about your background? You apparently started out in life as a physicist and then transitioned to computer science and AI. Maybe can you say a few words about why and how that happened?
Yes, actually a little bit more complicated. At some point in my life, I realized I was born already as a Bayesian, but I mean, we don't have to really dig into this. I always had discussions with other people, and before I knew about frequentists and Bayesians, and then later I realized, okay, most of people are frequentists because I mean they learned that at university and I'm Bayesian. So I always say, no, I'm born a Bayesian. But no, my interests from a very young age were twofold. One was understanding the universe, which naturally leads to want to study physics. And the other one is creating AI. So I toggled back and forth between, so I did the German equivalent of a bachelor's in computer science, then a bachelor in physics, then a master's in computer science, then a PhD in theoretical particle physics. Then I had a 4.5-year stint in the industry. But then I really wanted to return to do fundamental research, and sort of then since the year 2000, I finally settled to working on AI.
Okay. All right, great. Maybe one more question. What's the backstory behind your Hutter Prize? Why did you create it? Why do you care about it? And how did you secure the funds for it?
Okay. So the reason is, and essentially one reason, but sort of has multiple facets. As we will discuss in this podcast, there is a close relation between being able to compress data and being able to predict data. Actually, the prediction compression relation is in a sense perfect, right? There is no difference between prediction and compression. And being able to predict well is at least, I would say, half the rent for a general intelligent agent. So if you want to behave well in an uncertain world, you need to make predictions and then make plans and decisions accordingly. And if your predictions are bad, then even if your decision algorithm is good, your actions will be bad. So this connection is pretty obvious for a set of people who work on compression. Stochastic compression is peculiar, and it's now, meanwhile, since we have the large language models and they're trained on log loss. So this duality between compression and prediction now is becoming mainstream. But when I started the Compression Prize, that was not so well known, and I wanted to advertise that. But apart from advertising, I also want to solve the AI problem. And since prediction is one half of it, we need better predictors, which means better compressors. So I thought I want to encourage people to come up with better compressors because that is closely related to then prediction and AI. And as we will discuss briefly, probably, these LLMs are essentially, the models. The better they compress, the better they perform on downstream tasks. And with the securing of the funds, I made a big gamble. I mean, initially it was only nominally 50,000 euro. But you don't get the 50,000 euro in one go. If you beat the current state of the art by X%, you get X% of the price. And my reasoning was, either progress is slow, which I expected, and then I can afford to pay it out, or progress is sudden, then this is such a major event that I'm willing sort of, to scrape somehow the funds. And I mean, meanwhile, it's 500,000 euro nominally, but usually the improvements are, a couple of percent, every couple of years. So I only have to pay out, smaller amounts. And yeah, I mean, if suddenly somebody compresses to half size, then I have to take another mortgage on my house.
Okay.
But I will definitely honor my commitment. So don't worry about that. So far.
All right. I hope you'll get a flood of participants after our conversation.
Yeah.
Thank you, Marcus. Before we dive into the details, why don't we get an overview from you about the theory of universal artificial intelligence? You're responsible for its creation. Can you say a few words at a high level what it is and why people should care about it?
Sure. Yeah. So, okay, let me go back a little bit. As I said, I couldn't decide between physics and AI. Physics had beautiful math and elegant theories and so on, while on the other hand, I believe that AGI now has more impact, more practical impact. But at the time, at least in the 90s when I studied it, AI wasn't really, the field wasn't really too attractive to me. So that there was good old-fashioned AI with logical reasoning expert system, which was sort of reasonably formal. But I never believed that this is the way to true AGI. And then there were, of course, neural networks, but I didn't like the neural networks too much. And I mean, they work to some extent, but also not very well. And anyway, and I didn't have any good ideas myself. So I left the field, worked for 4.5 years in a startup. But after a while, after a couple of years, I couldn't stop thinking again about AI. And finally, more or less, in an instant, I realized what has to be done and what was missing. And to keep it short, many fields start out in an informal way, and then they get more and more formal, which helps sort of with the technical and the scientific development. I think about physics, the energy was a mysterious concept, and the kinds of things that now it's rigorously formal. But if you look at AI, nobody has really formally defined what intelligence is. But AI is about artificial intelligence. How can we work about AI if we don't know what it is? I mean, you can do it, but I thought it will be extremely useful to know what is actually the ultimate goal. And I mean, I knew, for instance, if you play chess and we play minimax to the end of the game, that is the theoretical optimal thing to do, right? So for perfectly well-specified environments, we know how to do this sequential decision in an optimal way. But the world is unknown and uncertain, and we have to do predictions. And I wasn't aware at that time neither about Kolmogorov complexity nor Solomon induction, but then I realized generalization via Kolmogorov complexity and Solomon, which is sort of rediscovered, but way 2 decades too late, is the way to go. And so what I discovered is, or rediscovered is, that you can make predictions of arbitrary time series, whether it is stock market data, weather forecasting, or number sequences 1, 2, 3, 4, 5, or any data. You can do that in a certain sense in an optimal way without knowing the underlying structure of the problem, using what has been known even at the time, Solomon induction, using Kolmogorov complexity. But that is only prediction, right? And agents also act. But I knew sequential decision which solves the action problem if you know the environment. And in hindsight, I put these things two together and arrived at a model which does optimal decisions in arbitrary unknown worlds. And if you think about this sentence, right, this is what AGI is or should be about. And that's what I coined universal AI, wrote down the mathematics, and in the last 25 years proved a lot of theorems about it. And we also approximated to some extent and implemented it. And so there's now even nice connections to actually large language models, and we probably a little bit talk about this. If there's somebody here listening who primarily or only cares about large language models. So they will be covered too.
Okay, great. All right, great. That's a lot to unpack. So I think probably the best way forward is let's just start writing a technical outline, because I think once we start getting into the details, more of this will become clear. So let's now go to the whiteboard, and I'll start with writing a list of topics that I think we'll be covering and following, and of course we'll adjust along the way. So the first kind of phenomenon we'll be discussing is what's called universal prediction, which is what you alluded to before. And, without loss of generality, what is the problem of universal prediction? Basically, we're given a sequence of zeros and ones. In general, it could be an arbitrary alphabet, but binary is sufficient to illustrate the point. We want to predict probability of next digit, right? So that's the prediction problem, and it's universal in that we a priori there could be any probability distribution governing the sequence of zeros and ones, and our job is to sort of discover that, so to speak, right? And so this is the universal prediction problem. If I see a stream of binary digits, can I use that sequence of observations to guide my prediction for the next digit that I see, right? And the way we're going to kind of go about explaining how to solve this problem will be through a few steps. The first thing we could do is start with the warm-up, which is to explain Laplace's rule of succession. So this is one of these, I guess you could think of it as a simple guideline of how to make the next prediction given the observations. But of course, there's a mathematical basis for this, and we'll go into that. And from that warm-up, which I think will be a very nice illustrative example to get people familiar with the problem if they haven't seen it before, the right framework, or the more general framework for this is Bayesian sequence prediction. So sort of Bayesian reasoning underlies all of this, and I guess maybe that's not a surprise given you said that you were born a Bayesian, but of course, you start with the prior, you make some observations, you update your beliefs, and just keep iterating on that, and we'll see how that also, how Laplace's rule is an instantiation of that. And sort of that sets the stage for talking about Kolmogorov complexity. Kolmogorov complexity, which philosophically, when we combine it with Bayesian reasoning, is a form of Occam's razor, as we'll see, right? Because Occam's razor is about keeping your hypotheses as simple as possible, and Kolmogorov complexity is a way of measuring complexity, and so we'll see how those two things are related and tie that into Bayesian reasoning. And you already mentioned Solomonov induction, so that will sort of be the highlight of this section, which is a way of combining Kolmogorov complexity with Bayesian sequence prediction. And in some sense, this basically gives us a way of solving the universal prediction problem, right? That's what sort of Solomonov induction does. So this is basically a very rapid overview of the first part, universal prediction, and then sort of.
Can I add two things?
Sure, of course, sure.
So here I would like to mention a few special model classes, which are bigger than just predicting sort of IID sequences, but small enough so that you can do that efficiently. The names will come later. And then after this, probably after, it's discuss loss functions.
Sure, of course.
Because it somewhat ties into the next section where we then deal with value functions, and loss is sort of more or less the same as value functions.
Sure. Right. That makes a lot of sense. Of course, we want to get to universal AI. So how do we get to there? So that brings in the second section, which is we'll talk about universal agents. And by agent, that basically means we're going to combine prediction from the previous section with planning, right? Because agents act. And so if if you have a model of your environment and you want to say optimize your reward, then that gives you a way of planning, right? And what we'll find is that when we kind of combine the ideas from the universal prediction side with action and try to get something that's optimal, we get a universal optimal agent, which has this nice acronym, AIXI, Artificial Intelligence Cross Induction, right? Maybe just to clarify that when we talk about why do we keep using the word universal because we don't care what the environment, or how to say, the environment can be arbitrary, just like the generative distribution for our sequence of zeros and ones in section 1 is also arbitrary, and so we want a solution that works for arbitrary or general situations, right? So that's
yes. And before we get to that, I have to first introduce agents in known environment. Agent.
That's right.
Known environment.
Okay, great. And then after we discuss those two, we'll just see what we have time for in terms of extra material, right? So there's a lot we can cover. Your books have lots of material, but just to list a few that we might cover, just depending on how much time we have, we can talk about, say, computable approximations to all of this, because for those who know, Kolmogorov complexity is not a computable function in the Turing machine theoretic sense. So of course, this is nice theory, but if you don't have something that's computable, maybe it might be limited, and so you want to come up with computable approximations. So that's something we may want to discuss. There's also maybe multi-agent settings where there's more than one actor, right? And maybe
the multi-agent, we should definitely cover multi-agent.
Okay.
I mean, we can be very brief about it. So it's
sure.
Anyway, I mean, this is related to the grain of truth problem. It's too great not to mention it.
Sure. Okay. And then finally, of course, any philosophical discussions about AI that might arise from these both technical and philosophical considerations that we're discussing here. Okay, so this sounds like a pretty good outline.
Yeah, maybe we should add for the people who are here for the language models that I will also talk a little bit about LLMs, but don't expect too much.
Okay.
But we have one recent paper which really ties it nicely together, the Solomonov induction and the LLMs.
Sure. Okay, great. All right. So why don't we go to the next page, and why don't you start us off with describing to us Laplace's rule?
Let's start with something super simple. Well, maybe just start with even simpler, frequentist predictions. I mean, we need a notation in this setting anyway. So we have a sequence, x1, x2, x3, and so on. And for simplicity, we assume most of the time binary, but everything can be extended to finite alphabet more or less straightforwardly. And to larger alphabets, that's usually I leave to the mathematician, because I think it's AGI irrelevant. It can be mathematically, of course, interesting. Okay, so I also use everywhere the abbreviation x1 to n, which is just the sequence x1 xn. Okay, so let's assume they are drawn IID, so from a Bernoulli theta process, right? And theta is in 0, 1, so that's a biased coin. If theta is not equal to half, it's equal to half, it's a fair coin. And we want to, I mean, most of the time in statistics, you want to do induction, you want to infer the unknown parameter, right? And, well, how do we do that? Well, we count the number of ones. In binary, I can just take the sum. Wait a second. So assume we have seen k once, and then n minus k is, of course, the number of time steps where xt is equal to 0, just a complement, of course. Okay, and the naive frequency estimate would just estimate theta as k divided by n, and from the large numbers, we know that it converges to, let's call it theta 0, if the sequence is sampled from IID from p theta 0. Okay. So long, so good. Most of the time, I will be concerned directly with prediction rather than parameter estimation, which has the advantage is that sometimes the parameter estimation can be harder than the prediction. For instance, if you cannot uniquely, if you have a model class, you cannot uniquely identify the parameter, you may still be able to do prediction well. So it avoids a lot of complications in more complicated classes. Here, in this simple Bernoulli class, there is no difference. So the probability under parameter theta that the next symbol is 1, given the history, right? This is just theta. So the predictive distribution is the same as the parameter. So it's the same. Okay. So why is this bad? Okay. And this is where Laplace sort of comes in. So he considered the problem of the sun rising. So he was at a certain age, I don't know how old, I don't know, maybe 30 years old. And so that means he has seen the sun maybe rising 10,000 times. And he asked about what is the probability that the sun will rise tomorrow again. I think he had another estimate where he estimated that the world had been 4,000 years old, according to the Bible. And so maybe around 1 million days. Yeah. So you have even more data that the sun rose every day. So what's the probability of the sunrise tomorrow? Okay. Let's look at the data sequence, the sequence x1 up to, x, say 1 million. Yeah. They're all ones. Okay. So k is the same as n. So we take the frequency estimate, k divided by n, which is just 1. So we would predict that the probability the sun will rise tomorrow is identically 1. So we are absolutely sure that the sun will rise tomorrow. And that feels, of course, way too overconfident. And he asked, how can we come up with a prediction which is more reasonable? So it should be something close to 1, but not exactly 1. And so let's derive Laplace rule. I present you the end result. The end result first was that he says we should predict this probability.
By the way, just notation-wise, 1 to the million means a concatenation of 1 million ones. Is that right? Your exponent?
Yeah.
Okay, not a little exponentiation. Okay.
Upper exponent has often multiple meanings. Yeah.
I see. Okay. I originally tried to correct it as plus because I thought you were looking at numbers, but I realize now it's just concatenation. So let me fix the whiteboard now. Okay. Good. So, and he said instead of using k divided by n, use k plus 1 divided by n plus 2. And if you plug in k to be equal n, that would be n plus 1 divided by n plus 2, which is 1 minus 1 over n plus 2. So if you assume the sun rose 1 million times, he would say the probability the sun rising tomorrow is roughly, not rising tomorrow is roughly 1 over 1 million. And at least that's not implausible, right? The probability cannot be much higher, right? If the probability of sun, and we remember that was at a time where people had no idea about the sun being a fusion reactor and exploding at some point in a supernova and these kinds of things. So this IID model was at least not totally absurd. Let's phrase it that way. And it cannot be much larger than 1 million because if the sun would rise, or fail to rise, more often, we would have seen it already. So it is sort of a lower upper bound depending how you view it. But maybe it could be even closer to 1 and you could argue about it. But now let me give you the derivation. And it's really beautiful, and I think everyone should know this. I mean, it is really one of the most basic applications of Bayesian inference and the most beautiful one. So we don't know this parameter theta. And frequentists deal with this in their own way. But the Bayesian just says, okay, we have an uncertainty over this prior theta. And we also model this by a probability. This is not a sampling probability, but this is objective belief probability or epistemic probability, okay? Usually I use the letter W, but you can also use P or whatever you like. And the indifference principle
tells us if we don't know anything, we should assume a uniform. Theta is continuous parameter in the interval 0, 1. So a uniform prior would be just equal to 1. Okay.
Actually, let's just back up for a second, because I don't know if you've already kind of alluded to what you said, but I think one thing that might be puzzling about this, if you haven't thought about it before, is if like what's wrong with assigning probability equal to 1, right? Because I've seen it a million times before rising, and so if I were just to obviously use the sample estimate, then of course for all past observations, the sun always rose. So I should just kind of duplicate that estimate, right? Like what's wrong with that?
Okay, first give you an example more close to home, right? I have a coin, right, which could be a fair coin, or it could be a coin which has 2 heads. Okay, I flip it 10 times, right? Let's say 10 times, and it always comes up head. Are you 100% certain that the next time is head?
That's right. Fair enough. There's still a small chance. Right now, you could have had a coin that had 2 heads on it, or you could have just gotten very lucky with a fair coin, right? So
exactly. Yeah. So in this case, of course, the probability is 2 to the minus 10, right? So the probability of it being the fair coin is very small. But maybe let's put in the mix a coin which is heavily biased towards head, right? It has a 90% probability of head, right? And now you see 10 heads. Well, there's actually, I don't know the numbers now, maybe there's a 50-50 chance it's a 90% head coin or the full head. So you should always reserve, especially if you allow more complex models, the probability that something. So that is actually a general principle. Everything which is not logically excluded, right, or by physical laws. But even physical laws may not be 100% certain, right? You should assign a non-zero probability to it, right? So to the event that the sun will not rise, it can happen, right? Why not, right? So you should assign at least a non-zero probability, and frequentists would assign a 0 probability. So they're just overconfident. You can view it from a betting perspective, right? The Dutch book argument: how much would you bet, right? Against or towards the sun will rise or not. Of course, I would easily bet 100 to 1 that it rises tomorrow, right? 1,000 to 1, but I wouldn't bet sort of, 1,000,000,000 to 1 or whatever, right? Maybe, because with sunrise, maybe then we are all dead, right? So we need maybe call it something like that. Anyway, never assign probability 0 except to logically inconsistent events.
Sure.
Guarantee event.
Okay, great. Yeah, and I think that's now a good segue into talking about this assigning a prior, because that's exactly, therefore, assigning weight to all candidate hypotheses that aren't ruled out by the data.
Exactly. So if we had just 2 hypotheses, right, fair coin or always head, it would be just, a priori we have no idea. We would say with 50% it's always head coin, and with 50% it's a fair coin, and then deal with it. But let's assume here, we have no idea about this bias of the coin, so take a uniform prior.
Okay, sure.
So now, before we continue, let me maybe present you Bayes' rule in the general form. You can present it in many forms. The most useful form is the following. Let's assume you have a class of hypotheses, Hi, I equal 1 to k or so. What does it mean? So these are point hypotheses, and they're mutually exclusive. So here what we mean is that the probability of your data, x1 to n, under some hypothesis I, has a certain probability distribution. So for instance, h0 could be fair coin, right? Then this would be just 1/2 to the n. h1 could be all heads. Then for the sequence all ones, that would just be 1, right? So this is just the hypothesis is just a probability distribution. We only care about sequences here over sequences here. Okay. Then we have a prior, or maybe at this stage I use the p so that it's more conventional, over the hypothesis. So if we had sort of fair coin versus head coin, right, it would be 50/50 or something like this. And I ask, what is my posterior, that's my prior belief, what is my posterior belief in this hypothesis after I have seen data, okay? And Bayes' rule says you should take your data, the likelihood function, and you multiply it with the prior, and then you need to normalize it so that it's a proper probability distribution. And this normalizer, let's call that P of x 1 to n, is just the marginal distribution over all this hypothesis. So that is called the Bayesian evidence, or the marginal distribution. Has many names. Partition function. Okay, and I mean, if you flip it around.
Sorry, just I think
on the left-hand side, I missed something else. That's a posterior here, of course.
Yes, that's right. I was going to say that. Yeah.
Good. At 1 to n. So if you flip this, if you flip the denominator to the left-hand side, you see it's just P of h given x is P of times P of x is P of x given h times P of h, which is just the definition of conditional probability. So there's really not much to it, okay? But so that's the great thing. If you're Bayesian, that's essentially the only thing you need to know. And you just always, you think about your prior, you come up with a model class, and then you just, crank Bayes' rule.
Right. So just to say this in a few words, right? You start with some, your prior is your set of initial credences as to how likely the individual hypotheses are. In this case, there's a hypothesis for each value of the probability that the coin produces a 1, right? So each HI is the theta, and then the likelihood is just a computation how likely the data is given that value of theta, and the posterior is saying, well, what is my new belief in the value of the theta's condition on the observation I just made, and that basically by the rules of probability theory, this is what Bayes' rule tells you how you should update your probabilities.
Exactly. Yeah. So now let's instantiate it. So this is completely general. Whatever your model, and there's no IID assumptions or something, or stationarity or Markov or something. So that is completely general. But let's go back to the Bayes to the Laplace example. So here, the class, we have not a class of finitely or countably many hypotheses, but continuum. So the only thing which changes is that the sum is replaced by an integral. Okay. And the hypothesis class is now, h theta, or just theta, with theta in 0, 1. Okay. Then my likelihood function onto n under h theta, or just abbreviate theta, is, okay, so let's assume there are k ones as before and n minus k zeros. Okay. So it's an IID model. So this is just the product over all p of x t equal 1 to n. Okay. What is the probability over 1? Well, the probability of 1 is theta. And how many ones are in this sequence? Okay, k. And the probability of 0 is 1 minus theta, and there are n minus k zeros in the sequence. So that is my model of a biased coin. Okay. And now the prior, as before, it's up here. Okay. So now we compute the posterior. Before we compute the posterior, we have to compute the denominator, which is always the hardest part. Sometimes it's impossible, and there are all kinds of very sophisticated tricks to still compute the posterior without the normalizing constant. But here it is very easy to do. Roughly speaking, it's also a rule of thumb. If you can compute the denominator, you can compute all other quantities of interest usually easily. So that's a rule of thumb. And we will see, we can actually avoid even looking at the denominator. So now let's compute the marginal distribution, so the denominator. That is, according to this formula, is integral over the likelihood times the prior, so that it's just in this difference. So this is just the denominator just written explicitly out for a continuous parameter. And well, we plug it in, so that's integral 0 to 1, theta to the k, 1 minus theta to the n minus k, d theta.
So this is the likelihood, right? In the integrand.
Yeah, the integrand, that is a likelihood times the prior, yes.
Yeah. So I just wanted to reflect that in the notation, just to be pedantic here.
Yeah, that is the same as p of x given h theta.
Yeah, so this should be a conditional on theta, I guess. Yeah.
Yeah, I mean, I have to put it. Sometimes I put it. Yeah, there's another side story. So if you're a frequentist, right, you don't have a probability distribution over theta. So you cannot condition on theta. Therefore, writing the likelihood as p of x conditioned of theta is, strictly speaking, syntactically or semantically wrong. You should write index theta or semicolon theta. So there's a whole paper by a philosopher, 30 pages, about this difference between semicolon, and bar, by Alan Hayek. So anyway, I'll get back to that in a second. But we really have to move on, I think. So sure. You can compute the integral, and this. So and this is the beta function, which is k of k plus 1 and n minus k plus 1. And the beta function is just a product and ratio of 3 gamma functions, but let's just skip over this. Yeah, so they're closed form, essentially. Okay, and the gamma function for integer values is, of course, just factorials. Okay, so now we can compute the posterior e of theta given x 1 to n, right? Which is just, I can write it. Well, okay, let me write it out. So that is a likelihood function, theta to the n, 1 minus theta to the n minus k, times the prior, which is 1, divided by this beta function, which is a constant. Okay. By the way, I will later sometimes just use this notation with a cross over the equal, which means apart from a constant. Okay. Okay. So the posterior is also this expression, and if you look now, so if you hear the parameter theta, which is between 0 and 1, and you ask about the posterior distribution. So before we have seen any data, so for n equal to 0, well, this is just the prior, and we are not sure what the theta is, so it's just this uniform distribution. But now, once we have seen a lot of data, and assume it was a fair coin, then k is about n half. And then if you look at this expression, it would look like this, a little bit like a Gaussian. So the probability concentrates around, well, 1/2 if it's a fair coin, and around theta 0, you can easily show that if it's a coin with bias theta 0. And the width is around of the order of 1 over square root of n. So, and then, this converges to the point estimate, as we all expect. Okay. But okay, this gives you the posterior, but Laplace asked about the predictive distribution. Okay, so he asked about what is the probability of x, the next symbol, given x1 to n. Okay, and there are 2 ways of computing this. So the standard way is we compute the posterior. Then I should start it differently. So I ask, what is the probability of xn plus 1 given theta? So if I know theta, what is the probability of next bit being 1? Okay, being 1 is 1, and being 0 is 1 minus theta. Okay, but I do not know theta, but I have a belief over theta. So I multiply this with my posterior belief over theta and integrate over this. Okay, this gives me the conditional distribution, and it is very easy to see that this is simply p of x1 to up to n plus 1 divided by P of x1 to n. So I could now do this, look at the posterior, plug it in. This is just the binomial, multiply with another theta, integrate it out, blah, blah, blah. But it is much easier to use this expression because, if you look at the conditional distribution P of x given, the history, well, by definition, it is just P of x1 up to n plus 1 divided by P of x n plus 1. Okay?
Mm-hmm.
And the denominator we have just computed above, right? This is this beta function, beta of k plus 1 and n minus k plus 1. And what is the numerator? Okay, let's ask what is the probability of the next bit being 1, okay? So we now look at the sequence, which is x up to xn, and then we have a 1, so the next bit is 1. So k, which counts the number of ones, is 1 more, okay? So the numerator is exactly the same formula, but k has increased by 1, so it's k plus 2 n minus k plus 1, okay? If you now plug in, the beta is 3 gammas, and the gammas are factorials, and everything cancels out, and as an end result, you get k plus 1 divided by n plus 2, and that is Laplace rule, which is very beautiful. Okay, so let me add one tiny thing. So Laplace assumed a uniform prior, and I don't want to go into details. There is reasons for choosing a prior which is slightly more heavy on the tails. That would be a beta 1/2 prior if somebody cares. I can write it down, but it's not really important. And this is called then the KT estimator. Maybe that's important, the KT estimator. And if you use this prior, then instead of k plus 1 divided by k plus 2, you get k plus 1/2 divided by k plus 1. Very similar, and sort of that is the modern version.
You mean n plus 1?
N plus 1 in the denominator, yeah. N plus 1. Yeah, which gives a very similar result.
Mm-hmm. Okay. Actually, can you say a little? This is something I actually don't know. Why would you have? I guess there's some optimality with this prior. So this prior is going to look something more like, as you said, it's going to be.
Yeah. So there are at least 2 different arguments for it. Yes, it will look like this. So it's proportional to theta to the minus 1/2, 1 minus theta to the minus 1/2. So it actually goes to infinity.
Okay.
At the end. And so there is 2 arguments. One argument is, so the uniformity principle says that if you don't know anything, you're to a uniform prior. But should I assign this uniform prior over the parameter theta? Or I can reparameterize my problem. Assume I instead of using the parameter theta, I use the parameter psi, which is theta square, which is also in 0, 1, right? And say I just parameterize it this way. I should use a uniform prior over psi, but then it's a non-uniform because of the formula how to transform densities. So this uniformity principle, if you apply it naively, is not so-called reparametrization invariant, which is bad, right? And the Jeffreys prior, if we want to go there, uses the following: uses the square root of the determinant of the Fisher information matrix. But let's move on, right? Whatever that is, right?
Yeah.
If you use this as a principle for assigning your prior, which is a little bit weird at the beginning, but it's actually has information geometrically has a lot of meaning. Then, if you do a reparameterization, you still get the same prior. So if you start with psi and compute the determinant of the Fisher information matrix with psi, then you get the appropriately transformed prior. The other justification is if you look at redundancy bounds or regret bounds, and you want them to be sort of minimax optimal, then this KT prior comes out of this.
Okay, I like the first reason, because you don't need to prove a theorem or know something sophisticated. It's just it's an a priori sensible thing to have reparameterization invariance. Yeah.
Yes. Okay. if people want to look it up, Bernardo is the prior.
Sure. Okay.
I mean, they are the same, but with the different justifications.
Yeah. Okay.
So let's see what we do next. So next, maybe we go to the general case of sequence prediction, right? We essentially already have everything. Yeah? There's not really much extra to do. So now we start with a model class M, which contains distributions, right? Before it was, H index nu or something like this. So nu of, maybe notation becomes a little bit more compact, right? So x1 to n is some probability distribution over sequences, okay? And I have a class of these distributions. And from now on, with some exceptions, I will assume that this class is, I have to write it differently, is countable, M is countable. Most of the time, so that I don't have to deal with integrals. And I take a prior over this class, and then I compute the Bayesian mixture distribution or evidence or partition function or whatever you want to call it. Psi1 to n is the same as before. Some likelihood times prior nu in M. And then I do predictions now also for notational convenience, I predict xt given up to t minus 1. So another x less t is x1 up to x1. Okay.
So let's just back up a little bit. Okay, so a lot of notation was written here. So first of all, M is our hypothesis space, essentially.
Yes.
In the previous example, it was actually not a countable space. It was the unit interval, because we had a hypothesis for every coin flip probability of equal to 1. Now we're going to simplify to countable, because ultimately we want to get to a regime where we want to say implement this on a computer, and of course the set of programs is countable. So that's kind of the restriction looking ahead, why we want to consider things that are countable. Correct.
Exactly. I mean, if it's uncountable, then you just replace that as the sum by an integral as before, and the prior is a prior density. But I don't want to constantly deal with the two cases and the countable cases.
Sure. And of course, and I think maybe just one step for clarity before we start evaluating these quantities on actual sequences. Really, your prior is without writing, again, it's evaluation inputs. You're saying my prior, which you wrote as C here, is say some weighted sum. I think in your book you used maybe a subscript.
Yeah, you always use the word prior. So Lomonoff used the word a priori distribution.
Okay.
But let's not even call it a priori. I mean, if you want to call it a priori distribution, the prior is W of nu. That's the prior, and the psi is, call it Bayesian mixture, call it Solomonov distribution later, call it universal distribution, call it Bayesian mixture, call it Bayesian evidence, call it partition function. Don't call psi prior.
So just to make our terminology consistent, so W is the prior and C is this mixture over the measures in M with respect to that prior.
Yes.
Okay, great. Okay, I'm happy with that terminology. Okay. And maybe one more comment. So you start with this mixture, and the formula you just wrote here, well, it's just the evaluation of that mixture on a sequence of length n, but what you were about to write is how you're going to update that mixture using Bayes' rule, essentially. I'm not sure that's the best way to say it, but yeah.
Actually, I mean, you would update the prior to a posterior, right?
Mm-hmm.
But as I said, I want to skip the posterior and directly consider the predictive distribution.
I see what you're saying. Yeah.
And there is no real update. Sort of Bayes does all this under the hood, right? So it is just, you have your mixture distribution and you take the ratio of psi of, so again, let me write it down, psi of x1 up to t divided by psi of x less than t. And you could write it as an integral over, posteriors and like blah, 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 and so on. But, this is all gone now. From now on, I only consider predictive distributions. Maybe at some point the posterior will pop up again. But mostly I'm interested in prediction and not induction.
Yes, I see. Basically, yeah, I mean, this kind of came up also in our Laplace example. You could keep track of the intermediate quantities in terms of the prior and the iterated posteriors, but that all gets absorbed into under the hood, as you said, when at the end of the day, if all you care about are these predictive distributions, that's implicit in everything, but you never need to explicitly kind of keep track of it. But it's there if you wanted to recover it.
Exactly, yeah.
Yes, yeah, okay, great.
Okay, good. So now we have this predicted distribution. And so before, in our very simple model class, we showed that this converges, or that this predictive distribution was Laplace rule, k plus 1 divided by n plus 2, which converges, of course, light frequent is asymptotically to the true parameter theta 0. Okay. Now we have made no assumptions about this news, about this probability distribution. So one could be, for instance, a distribution which is 1 on the digits of pi, right, and 0 on all others. So it's a deterministic environment which produces the digits of pi, right? And there's no statistic. Or it could be 0, 1, 2 zeros, 1, 4 zeros, 1 or something. So anything you want. So there is no notion of convergence to a parameter anymore. There is a sort of parameter underlying the nu. We could talk about it. But as I said, I don't want to. But we consider the predictive distribution. So we can still ask questions like, assume the data x1 to infinity is sampled from the distribution mu, and the true distribution I call always mu. Before it was theta 0. Theta 0 is usually the true parameter. And here mu is always the true thing. And let's assume it's in the model class M. Okay. So if we know mu, so x is sampled from mu, we cannot, if it's stochastic, we cannot deterministically predict bits like in a coin flip, right? But we could ask, what is the true probability of the next bit given the history, okay? In the Bernoulli example, that would be theta 0, okay? But we don't know mu, so let's use the Bayesian predictive distribution psi for prediction. Let's use this one instead, because this we can, in principle, compute, okay? And now we can ask, how close is this to the truth? Okay. So let's take a square. And so it would be nice, if we somehow could converge, prove that it converges to 0. Well, of course, it will not converge to 0 on all sequences, only on sequences which are sampled. So maybe almost surely. Yeah?
Maybe let's just say a few words, because if you haven't seen this before, it's maybe a little bit abstract. So mu is this true probability distribution of the sequences you observe. You don't know what it is. What you do have is this mixture where you decided what the weights were in advance. Is there how do I say, playing devil's advocate here, is there a way to, why should I expect the C to converge to mu?
Well, okay, I can give you some intuition. I could even present the proof, but I want to move on, or maybe at least some steps of the proof. So first, let me write down the result you can prove. Okay, so you can prove this result, and I'll come back to it in a second. But you can prove something much stronger, and the way actually you prove this convergence result is via the stronger result. That's the reason why I want to present the stronger result. Okay, so you cannot. In the IID case, we could prove a rate, right? So the psi deviates from theta 0, and the rate is sort of 1 over square root n or whatever, right? But in the general case, you cannot prove a rate in this sense anymore. But what we can do is, okay, first we take the difference squared, then we sum over all time instances up to infinity. So we take all the deviations and sum over it, okay? And then we can show, I fix it in a second, that this is finite, okay? Well, it's not finite for every sequence, but it's, almost surely or in expectation. So we take the expectation over this with respect to, of course, the true distribution, okay? So now what we have here is we have an infinite sum of non-negative quantities, which is finite. And the only way that this is true is that this difference converges to zero. But since there's an expectation in front, this converges to zero only almost surely. So why does this bound hold, right? And that is Solomonov's main result, which he proved in 78. And first, I mean, we have here, and by the way, this is also not the very exact formulation, but I mean, it's actually true in this form. But okay, anyway. So let's take some abbreviation, psi t and mu. So psi t is psi of x t given x less t. I don't want to write this out always. And the same, of course, for mu t. Okay. So what you have here is you have the square distance between psi t and mu t. Okay. You can show it's a version, say, of Pinska's inequality, that the square distance is bounded by the KL divergence between mu t and psi t. I give you a more down-to-earth sort of intuition for a finite class in a second, but that's the formal proof. So the square distance is bounded by the KL divergence. So we have a sum over t. I mean, this is super sloppy here and lots of things are missing, so the expectation and so on. So the KL divergence has a telescoping property. So this is the same. So if you sum only up to n, not to infinity, then this is the same as the KL divergence between the x1 to n given psi x1 to n. So I mean, this telescopic property is well known. And if we write this down, then this is sum over mu of x. I really didn't want to go into this detail. ln mu of x1 to n. So let's be quick, and then I give you the more intuitive, but that is sort of the proof. So this is this. And if you look at the Bayesian mixture formula above here, so you still have this slide here, the psi was defined as a sum. So if we drop from the sum all terms except mu, so we get mu of x1 to n. Do you see this, what I'm writing?
Mm-hmm, mm-hmm.
Okay, so I just drop all terms except for the true environment, so that's definitely larger equal.
Yep.
So now, if I bring w to the left-hand side and psi to the right-hand side, you see that mu divided by c is upper bounded by 1 over w. So this one here is upper bounded by w mu to the minus 1. Okay, that's from the above inequality. And this sum, so this is now a constant, and this sum is just summing the probabilities over arbitrary sequences. This just gives you 1. So this bound, and there's a logarithm, don't forget it. So this gives the logarithm w mu to the minus 1. And as long as the prior is larger than 0, then this is, of course, smaller than infinity. Okay?
Sorry.
So that's the derivation.
I see. Sorry. N is fixed here, and you're summing over all possible sequences?
Yes, all possible. Yes, that is all possible sequences x1 to n for fixed n. So this shows you that for a fixed n, this is bounded by this constant, but this constant does not depend on n. So now I can let on the left-hand side the n to infinity, because here I started with s infinity. Let's call this s infinity, but then I proved only that Sn, where the sum is up to n. But, you know, since the right-hand side is a constant independent of n, I can just then, once I'm finished, take the limit n to infinity on the left. Okay, let me get to the intuition. So let's assume m is finite and contains m is not used up, m elements, and we choose a uniform prior. W of nu is 1 over m. Okay. What you're doing is, I mean, this will be informal now, but you can also formally prove it. So you're mixing uniformly over your environment in the class, and you're making a prediction, and that is very close to a weighted majority, right? I mean, if the majority of distributions want to predict 1, you will predict 1, okay? So let's assume it is a majority voting, which it is not, but it's close. And let's assume the majority is right, predicts the correct thing. Yeah. Then we don't suffer any loss and we are happy. Okay. Let's assume the majority is wrong. We make a wrong prediction. Then we get, in the next time step, we get a feedback this prediction was wrong, so we can exclude this from the class if it's deterministic hard, if it's probabilistic soft. So this class got halved. So for every prediction error we make, we halve the size of the class. Okay. Once the class is down to just containing one element, namely mu, the true distribution, we are done. Okay. So how many halvings can we have? Well, we can just have at most log 2 m halvings, right? So the number of errors is roughly bounded.
I see. So this is the deterministic case where your measure is concentrated on a
Yeah.
single, the prefix of a single sequence. Yeah. Okay.
And log 2m is just minus log 2 w to the nu to the minus 1. So apart from sort of an LA2, you get the same result in the deterministic case with uniform prior and finite clouds.
I see. Okay.
And then you have to make it for non-uniform prior. You get these weights, and it's still the intuition goes through. Then you have to go to stochastic models, and then we don't really use a weighted majority because we use a weighted mixture. So there are differences, but the intuition is the same.
Sure. Okay. Let's just take a step back because so this gives intuition about that bound. But I guess the very high level non-mathematical intuition is essentially let's go back one slide here. What these bounds are saying is that as you make more and more observations, your mixture predictive distribution will converge to the true one. Because for several reasons. One, you assigned non-zero weight to every possible hypothesis, so you don't exclude anything. That was this Epicurus principle that we discussed earlier when doing Bayesian inference. So that's one prerequisite. And the second thing that's happening is, as you just alluded to, as you make more and more observations, the ones that are inconsistent or improbable with respect to mu in general get downweighted, and the things which are more consistent with mu get upweighted, and that happens in such a way that asymptotically you have to converge to mu, your predictive distribution.
Intuitively, exactly right. We can even write it down like before. So let me write it down here. So we can write down this psi of xt given history as what I wanted to not do anymore, but let's do it anyway. As nu the posterior w of nu given x less t, and then times nu of xt.
So you use the Bayesian update rule to compute those revised w's, those weights, and what you'll find is that those weights go up for the things which are consistent with mu, and those weights go down for the things that are inconsistent or improbable.
Exactly. And in very simple cases, this posterior would just on the true distribution, it would converge to 1, and all the wrong distribution, it would converge to 0.
That's right.
In this more complicated setting, maybe there are two distributions which are totally consistent, right?
That's right.
They can always, but the total weight on the distributions which are consistent with the data converges to 1, and those which are inconsistent converges to 0. That means effectively, in the simple case where there is a single distribution where it concentrates to the true distribution mu, this sum just collapses and gives you mu of xt given x less t. But proving this via the posterior in the general case is hell, and this we will not talk about it.
So what's next?
Okay. Next, let me instantiate that. That was now. Before we started, it was simple model class like a biased coin. Now we have a completely general framework. We could plug in any model class we want, and we have this bound, right? So let's instantiate the 2 or 3 interesting classes which are important because they are bigger, so more interesting, but still tractable, so it can be computed in a fast way.
Okay, so you're going to look at now interesting M's, this family of hypotheses.
Yeah.
Okay, yep,
Okay.
yep, okay.
And
Yep.
I have shown you this bound on the last slide. If we have, and that holds for any countable class,
Okay.
but if we have a continuous class, right, back to it, and again, the proof is hard, and I don't want to do that. If you have a continuous class with d parameters, so let's assume M sort of is a class nu theta, where theta is, say, a d-dimensional parameter. Okay, now. Okay. And then you can show a similar bound. There you have to make some smoothness assumptions, but you can show a similar bound, and the bound is then ln w of theta to the minus 1 as before. But now this is a density. Then, because it's a density, we have d half ln n term, and this grows with ln n, so this dominates, so this constant could be avoided. And then you have the logarithm of the square root of the determinant of this mysterious Fisher information matrix plus terms small o of n which converge to 0. Don't worry about all this. The dominant term is this one here, and we just ignore this one. This is a constant, this is a constant. So it's just d half ln n. So the rest you can forget about it, okay, if you have a continuous class. And in the Bernoulli theta case, d was 1, and the bound would be 1/2 1. Okay. And the intuition is, if you have a continuous parameter, you could discretize this parameter and just take, so we know that we can estimate a parameter to accuracy 1 over square root of n. Yeah. And to encode a parameter to 1 over square root of n accuracy, you need 1/2 log n bits, right? So that is one way of interpreting this bound. So each parameter gets discretized to the accuracy which is needed and no more. And then this gives you, we haven't talked about code length yet, but we will get to that. So if you view it the second time, you will understand what I mean with this. Anyway, just trust me. So this is the bound. So for instance, a more interesting class than IID would be a K-order-Markov model, okay? So that means that the probability of xn plus 1 depends on xn minus k plus 1 up to n. So the last k parameters, okay? So how many parameters are they, right? For each context here, so assume alphabet size is x, or bar x, right? The context length k, so the k, x to the power of k possible conditions, right? And then we predict xn plus 1. And, well, this could be, out of x, but they have one probability constraint, so that is x minus 1 parameter. So in a binary case, it would be 1 parameter. If you have a ternary case, it would be 2 parameters and so on. So that's the number of real-valued parameters you have in this model class. So our D is this one here. Works as before. We just take the bound, you plug this slightly larger D in there, and that's the number of prediction errors you make, roughly speaking. Okay? Nice class, K-order-Markov. But if K is large, you see it's exponential in K, and it's no good. So there is a class which I think everyone should have heard about, but many machine learners.
Sorry, are you making the point that in this generalized bound you had above with D and log n, that D is for the kth order Markov chain? That's the D that you use, this formula that you wrote?
Yes.
Okay.
Yes,
okay.
yeah. Because that's the number of parameters I need to specify a K-order Markov process.
That's right. That's right. Mm-hmm.
Okay. Okay. So there's a K-order Markov process. But now I talk about very briefly something, context tree weighting algorithm. Okay. Okay. So what this
maybe
does
be very brief. Okay.
Yeah. So what this does is we Okay, very briefly. But we need it later if we come to the approximations. So what is this? Is essentially a variable order Markov process. So what you're doing is now, instead of using, say, two last symbols, you use, maybe if the last bit was 0, you maybe need another bit to differentiate it, whether it's 0, 1. But if the last bit is 1, you're fine. You don't need to see further bits in the past. Okay. So you look at these trees, and these trees have, of course, parameters, right? I mean, sort of, if the context is 0, 0, you have a parameter. If the context is 1, 0, you have a parameter, and if the context is 1, is a parameter. You also have a number of parameters. Okay. So for a fixed tree, you do the same as before, and what you get is, well, D is just the number of parameters. Let's call that the set theta is the set of your parameters, and then it's just the size of this parameter set. Okay, nothing changes. Okay, for a fixed tree. But if we don't know the tree, what we would like to do a Bayesian mixture now over all possible trees, right? Maybe of maximal depth D or so. Okay. So we just take the class of trees. So T is trees of depth smaller or equal than D. Okay. Then we need a prior over trees. We can do that somehow. So you can encode a tree in bits and take 2 to the minus the code length. We will get back to that later in a more general context. Tree as your prior over trees. You have, of course, you have the prior over the parameters, where you take your either uniform distribution or the KT one, which we discussed before. And then you do this huge Bayesian mixture over everything, so that the sum over all trees of depth at mod T, the sum over all, once you fix a tree, over all the parameters which are in the tree, and then you have your distribution, which is then the some distribution x1 to n given the t and the theta. Well, the sum over theta is, of course, an integral for sum, and then you get your distribution, whatever you would call it, it's t distribution.
Okay, so is this where this beautiful fact comes in that, okay, if you were to do a naive Bayesian update, you have to update, this, I don't know, double exponential count of weights, because that's how many trees there are. But if you only care about updating the predictive distribution, there's a very nice algorithm.
Actually, it is you can update the predictive distribution efficiently too, but it's much easier to update the joint distribution and then take the ratio. So even the joint distribution is easy to calculate if you calculate it in an online way. And let me just write it down because it's so easy. So yeah, if you would do that, I mean, the integral is easy to do, which is just lots of local little Laplace rule. But the sum is hell, as you said. This class T is about 2 to the 2 to D, so it's double exponential in D. But we can compute it in linear time in D, and we do that the following way. So let's consider a distribution x1 to n, but we don't code the whole sequence. We only look at the bits which have a context, meaning the previous bits, to be a certain string S. For instance, could be, if you look at this tree here, could be 0, 0, for instance, right? Or previous bit 1 or something like this. So S is a short string, okay? And how can we predict? Well, we could just ignore the context and just use this substring and code it, IID or with KT estimator. So the little index S about the X means the substring which has the context S. That's one way, but that's very primitive. The other way would be, well, let's look at actually a little bit longer context, so 0S, and predict it. And then you look at the other ones where the context was extended by a 1 and predict it. And we mix both of this with 1/2, 1/2. Okay? I mean, it is, you need a couple of hours at least, or days to understand this well. But I mean, this is the formula which you actually compute. And then, I mean, this is recursively going down So if the length of S is smaller than D, and if the length of S is D, then you just stop with the KT estimator.
Okay, this is quite advanced. We might
and I'll stop in a second.
Yeah.
And then if you take the empty context, so the CTW distribution as defined above is, I just write it here, is equal to P, the empty string of X1 to N. Okay, so you do this recursion, and then at the top end, you get the CTW distribution out. And there's a proof and blah, 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 so let's not go into it. But so this is a very rich class and a very powerful one, because if your source is sampled from a variable or amount of process, sometimes in the long context, sometimes in the short context, it gives you essentially the base optimal predictor for this very rich class very fast. And indeed, as we mentioned at the beginning, prediction is compression. This has been used for data compression and is among the best possible, clean compressors. Practical compressors, there's all kinds of extra sort of stuff around it. But if you look at the raw ideas, say Lemple-Sif or so, it beats Lemple-Sif like magic.
Okay. Okay. In the interest of time, should we get to Kolmogorov complexity?
Yeah.
Okay.
Yes. So this class was it's sort of the largest class which you can still compute fast. At least the largest class we know of. Okay. So now let's go to larger classes. And before we do that, we have to introduce Kolmogorov complexity. But I can do that very briefly if we don't need much about it.
Okay.
Okay. So generally, let's step a little bit back. In science, we need a principle which is called Occam's razor principle. So if you have two hypotheses which are equally good, describe your data, you should choose the simpler one. And there is no way around it. Without Occam's razor, there would be no science. Believe it or not. Well, it's argued in my book and in many of my papers, so no time for that here. Okay, but what does simple mean? We have to need a quantitative notion of simplicity, and we want one which is, for AGI purposes, which is universal, right? Which is not sort of limited to some, nice classes or something like this. And Kolmogorov complexity does that for you. So think about any object. You code it naively as a binary string. Think about now all data are binary anyway, right? And you ask, what is the information content in this string? Well, if it's a string of all ones, right, it's pretty boring, right? But if it's, pi, it's a little bit more interesting, but it's a very easy description. If it's a picture from a camera, there's a lot of information in there. And we can capture this by how difficult is it to describe my data? Well, we need a description length. Well, let's just take a programming language as a description length, anyone, C or Lisp or whatever you want. Or abstractly, we take a universal Turing machine because, that is also a universal description language. And we look for descriptions of our data. Okay, so let's take this universal Turing machine or your Lisp or your C compiler, whatever you prefer. We look for a program which, if you run it, gives us our string x1 to n. Okay, but there are, of course, many programs which produce a string. For the digits of pi, I can just write print quotation mark 1 billion digits of pi quotation mark. It's a very long program. But there are also shorter programs. And we want to Occam's razor asks for the shortest program hypothesis theory model of our data. So look at the length of the program and find the shortest one. Okay? And the length of the shortest program is called the Kolmogorov of X. And that's it. Okay? And, I don't want to argue here why this is a good measure. You can read it elsewhere. Okay? And we're going to use that. What you can show is that it is nearly independent of the choice of the universal Turing machine. So if you take code with respect to one Turing machine, or you compare it to K prime with respect to a different Turing machine, and you take the supremum over all strings, this is bounded by a finite constant. So if you have strings which are longer and longer, so even over all n, So if you have longer and longer strings, still the difference is just a constant, which is the typical compiler constant between compiling from, say, U to U prime or from Lisp to C and so on. And I mean, our data is so much richer and larger in AGI than this compiler constant that you can ignore this problem. Second problem is the incomputability. What you do now there is, okay, this is looking for the shortest program, which looks like compression, okay? So if we have data and we create a self-extracting archive, which means it's a compressed version, but it always also has the decompressor built in. What is a self-extracting archive? Well, a self-extracting archive is a program, if I run it, reproduces my data. Yeah. So what I can do is I can replace the Kolmogorov complexity by, the best self-extracting, the shortest self-extracting archive, which I currently can create with practical compressors as an approximation. Okay. And how do we use this? Why do we care about this here? Well, it quantifies Occam's razor, which is really great. So that it was for strings. If I have any other object like numbers, I can encode it in strings, right? If I have a probability distribution which is computable, right? There's a program which computes it, and I just take this program. So any object O can be coded as a bit string. And then the Kolmogorov complexity of an object O is just defined as the sort of some canonical encoding of it, and you just drop it. Okay. So because I will now,
maybe just one time. Yeah, I mean, I guess we're always working over countable things, which is why this is possible. Because of course, there's only countable number of strings and Turing machines. So of course, like when we were talking about probability distributions, by restricting to probabilities over finite length strings, then we're in a countable situation.
Yes, for probability distributions, we only look for computable probability distributions now, right? Mm-hmm. That means, by definition, they exist a program. That means there's only countably many, okay? Mm-hmm. And then we write K of nu for a computable probability distribution, and that's used mu for the class of computable probability distributions, okay? Mm-hmm. Technically, it's lower semi-computable semi-distributions, but let's not go into that.
Okay. Mm-hmm, mm-hmm.
Okay. So now we have a measure of complexity of a distribution, and Occam's razor tells us take the simplest one, but the Epicurus principle tells us keep the all, and we can unify these two principles and say, well, have a higher prior belief in the simple ones and a lower one in the more complex ones, and the same with the posterior. So don't rule out any. So we choose a prior now. Before it was left unspecified. Now we choose a prior, which is 2 to the minus the Kolmogorov complexity. And so that is monotone increasing what you want, and you choose 2 to the minus k of nu because you want it to sum to 1, or at least to be bounded by 1, and you can prove that this is the case, because a prior needs to sum to 1, right? Or at least not more than 1. So we now have fixed, let's call it W nu. We have fixed the class to be all computable probability measures. And for the expert, please forgive me that I'm a little bit crude here with some things. And we have fixed the prior. Well, and we can use Solomonov's bound for this. So the Solomonov bound was as infinity was bounded by, so let's plug in this. So we get the psi over this class, let's call it psi u. And the bound was the logarithm w to the minus 1. And if you plug in this is just k of nu times ln2. So this is now actually Solomonov's bound. That is what he's proved. Okay. And
no, this is nice because this is saying basically, simpler hypotheses have fewer mistakes on average. Right.
Exactly. Even more precisely, if you have a hypothesis, a model, which you can encode, specify in 500 bits, then roughly speaking, Solomonov reduction makes 500 prediction errors, and then it's good. You never can tell where. They could be at the beginning, they could be dispersed out, but you roughly only make 500 prediction errors, and then it's good.
Yeah.
I mean, the real result is that you get closer and closer, you get proof sort of the number of epsilon errors is bounded by k of nu divided by epsilon square and blah, 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 and so on, right? But roughly speaking, and that is also intuitive, right? If I have an unknown world, which I need 500 bits to specify, I need to learn this 500 bits somehow by trial and error, right? So I need to make 500 mistakes. And you can indeed show that it's the best possible bound.
I think what's good to emphasize, because I don't think I appreciated this the first time, is that there are many priors you can write, because the only condition on being a prior is just that each W nu is positive, right? You want to assign positive weight to any candidate hypothesis, and the bound you wrote a few slides ago could have been any such. We could have used any prior, and the C that we had was the mixture obtained from that prior. What's special about the prior that you just wrote here using the Kolmogorov complexity is the fact that it has this sharpness with respect to this bound that I want you to maybe explain a little bit. What's the optimality for this?
Yeah. So what you can show is that this W U of nu, yeah. So you take any other prior over nu, it's computable. I mean, the non-computable priors, I mean, we cannot deal with anyway.
Okay.
Computable prior. What you can show is that apart from a multiplicative constant, this W U of nu is larger, which means that apart from this constant, minus log, right, is smaller. So if I take now log W nu, the minus 1, then this is smaller than log P of nu to the minus 1 apart from an additive constant. Because the log makes a multiplicative constant, additive constant. And these constants float around anyway. In Kolmogorov complex, you always have to do with compiler.
Sure.
So apart from this constant, this gives you the best possible bound.
Sorry, what is this lower bound you wrote up to a constant? What that is? So what's the statement?
The statement is that if you choose any other computable prior, it will be smaller than the universal prior apart from a constant.
Okay, because if it's computable, this is an intuition. I don't know if it's correct, but if it's computable, then you have to use a program that's basically lower bounded by the Kolmogorov complexity, and then 2 to the minus that is smaller, right?
Yes, that's the proof, right?
Okay, all right, I see. Okay, this makes sense. Okay, I see.
Okay, so it is what if your data is sampled from any computable distribution? And let me rephrase: it can be the digits of pi, it can be a piecewise non-stationary sequence, it can be a chaotic sequence or whatever, as long as there is a program of B bits which computes even stochastically, right, your sequence, Solomonov will learn it in the minimal number of errors.
This makes total sense now. This is very beautiful. Yeah.
Okay, so this was a little bit heavy, maybe. There is a different represent. So this is called this Xi U. This is called the Xi U here. Xi U is the universal distribution. But Solomonov derived a different distribution, but which turns out magically, which is equivalent. And this different one is, I mean, we had a lot of machinery now going on, right? And, base, and then, Kolmogorov complexity and all this kind of stuff. There's a shortcut to get to this. And I would like to present this shortcut in a short way. So what you're doing here is
so let's just pause. This psi u is the Solomonov prior, right?
That's the Solomonov a priori. There's 2 different definitions and versions, and this is one of them.
That's right. Okay.
Yeah. Usually I attribute the other one more to Solomonov, but sort of he came up with both in a sense. Okay. So, so the other one is you take a universal Turing machine, and which has an input tape and an output tape. And by the way, I'm skipping over so many things. You need monotone machines and so on. So, but this is all precisely in my new book. So we have an input tape, and we sample a uniform random noise, so fair coin flip, on the input tape. Okay. So this Turing machine sometimes will do something, sometimes nothing. So there will be a probability distribution on the output tape. Okay. And let's just call this distribution M of X. whatever that is. But there is a probability distribution of output tape. Okay? And it turns out that m of x is the same as psi of x. Again, you can be more precise, either with an multiple constant or for every m there exists a universal Turing machine, so the psi u is equal. So I have a whole paper about this, but essentially it's the same. I will not prove it here. The proof is, long and difficult. I give you a little bit more formal definition of this. What does it mean actually? So we're looking, the input tape is bits, but they are sort of programs. You can ask a question in a second. So this P is input bits, okay, on the Turing machine. And we then run the Turing machine, okay, on P, and then it outputs something. If it doesn't output x1 to n, we don't care. We only look about programs which output x1 to n, okay? So assume there's one program which outputs x1 to n, and only one. Because this program has length L of p, the probability of sampling this program from fair coin flips is just 2 to the minus L of p, right?
Mm-hmm.
Okay, but there will be many programs which output x. So we have to sum over all of these programs to get this output probability. So this is exactly the same as sampling infinite random noise and piping it through a universal Turing machine. This is sort of the formal definition here. And then these programs don't need to hold the star indicator. The programs don't need to hold that. That is fine. And and you can show highly non-trivial that these are equivalent. And that is really nice. So here we only consider deterministic programs predicting strings and mixing over them with a prior, which is 2 to the minus L of p. But the intuition, roughly speaking, is that these stochastic environments are sort of living in the convex hull of the deterministic ones, so are implicitly already included in the deterministic. So you only need to mix over the corners of this infinite simplex in order also to get the middle one. But I mean, this intuition is an intuition, but strictly speaking, it's not right. But anyway, right. but the statement is correct.
So we define Solomonov prior, the Solomonov mixture distribution in terms of Kolmogorov complexity. You gave this alternative definition. What Solomonov induction essentially is, it's the Bayesian sequence prediction when we start off with the Solomonov prior, right? And it has optimal theoretical guarantees. That's what's nice about the Solomonov prior. Okay. So why don't you describe the two other things you wanted to discuss in this section?